Swayam Prabha. Digital India. Educated India.
So let's go ahead. We have a lot to do. So what we have been doing is that we are doing some acceleration analysis of acceleration and the velocity. That's a kinematic analysis of some connected bodies. And in that, there's one last example where some of the bodies are actually also rotating. And the connection is such that that point is not really a fixed point. Let me just tell you. So we are doing the kinematics. Yeah, so we are looking at another type of connection. And all along we have been seeing this kind of where we have a number of bodies. And here there's two bodies, 1 and 2, the links, and they are connected at B by a hinge. So a hinge is a common point. This B point is common to both body and 1 and 2. And what it is that the B, the velocities and the acceleration of this point B, whether you consider it as a part of 1 or whether you consider it as a part of 2, it will have the same values. So this is what we have been doing in several configurations. So the piston may be moving in the horizontal, or maybe moving vertically, or maybe moving at some angle, or maybe moving in some kind of circle, and so on. So different applications are there. So, but however, the bottom base point is that the connections are at hinges. Okay, so we would like to do some applications where we have connections are such that it is not a hinge, a pin type of connection, but we call it as a sliding connection. Okay, a sliding connection. So what we have in mind is that this link A and B, I'm going to take an example. So here, I'll take this example. Or, okay, so one example we have here is that this crank and connecting rod, I'm going to put it in different manner. You would have seen this application. So this is a this is one example. Have you seen it somewhere? Well, if you have done the workshop, then this is a mechanism where this is called a quick return mechanism. So in which, in fact, the connections are C, B, D, and E here. In fact, this ABC is one system of connected bodies. Okay, so that means that if this is rotating in some manner, so this is going to, this point B here is not a hinge on the CD. CD is one link, whereas this B has a slider here, which is going to move in a slot on the link CD, so which you call it as 2. So in the link 2, there is a slot here, and then this point B is going to move up and down. So you can see that as this keeps moving up and down, this point B is going to slide. And so if you call this as B prime, which is on link 2, so this B prime itself, this contact point here is no more constant like a hinge, but this B is going to slide in the CD. And then once this is going to rotate, then this link is extended up to D, and from D we have another, so this CDE is another set of connecting system of connected bodies. Okay, so once you solve for the velocity and acceleration of this link, angular velocity, angular acceleration of this one, so then you can find out what D is, and from once you know the velocity of D and acceleration, then you can go and find out what is the velocity of E. So the advantage here is that this is interesting. So let us see, this is the crank here. I'll just tell this example. This is also a part of one of your tutorial examples. So if you look at this one on a smaller scale, so if you see this crank 1, which is, say, assume that it is having a uniform angular velocity omega 1, what it's going to make here is that as it keeps making these revolutions, so it is going to make this link 2 to 2 extreme positions. So can you see that the 2 extreme positions are like this? So the extreme positions are the tangent to the circle here. So 2 goes from 2 to 2 prime. So as this keeps rotating, so it keeps pushing it out, okay, during this. So it is going to go like this. And during this part of the motion, so it's going to retract this one from here to here. So these are the extreme points. So it is going to go from D to D prime all the way. So the thing is here is that now this crank 1 is having a uniform angular velocity with uniform speed, but this link 2 is going to go like this one slowly. So how much? It is going from here to here. So let us say this is P, Q, R. And let us say, so this PQR is a bigger arc of the circle and RSP is the smaller arc of the circle. So in this PQR, so it is going to go in this direction, and during this RSP, it is going to go back to this position. So the time taken for this kind of motion is governed by this angle. So this theta 1 and this is theta 2. So during theta 1, it's going to have a rightward motion. During theta 2, it's going to have a leftward motion. So the angles, if it's going through a uniform angular velocity, so the time taken by theta 1 is theta 1 by omega 1, and time taken for this stroke is theta 2 by omega 2. What happens is that this has a very important application in the case of machining. So what it is done here is that this is the reverse of this one. So if you think that this is connected here, and then here we are going to have this is some workpiece here. So during this motion, it's going to go this way and it's going to cut the workpiece here. And that's where you require a lot of force and it should be done slowly. Whereas in the return stroke here, so there is no cutting that's taking place here, and then it can be done faster. So this mechanism is called a quick return mechanism, which has one of the main applications is called the shaping machine, the shaper, which you use in the workshop. Okay, so maybe you'll be using it. So where the cutting stroke is done slowly and the return stroke, which is the kind of ideal stroke, is done faster. So during this theta 1 angle, so it is done slowly with a lot of power and slowly, and then this return, this RSP, so that is the one when it is going to do faster execution. Okay, so this is this kind of mechanism. So that's exactly what this is going to do. Okay, so here also exactly. In fact, you can find out what is the angle theta 1, what is the angle theta 2. So it all depends upon this is the crank. And so you can say that this is the tangent here. So this is 90 degrees. So you can find out what is this angle. And then you can actually calculate all the forward stroke, time taken, and return stroke, time taken. Okay, so this is one of your tutorial example problem also. So now let's go and do the analysis here. Okay, so this part I'll remove. Well, this is the application. This is what quick return mechanism is. So in this, the most important thing is that this point B is a hinge on the slider, but then this slider is going to move up and down. Okay, so if you want to analyze it, then so there are several points which we are going to depict here. B is a point on the crank 1, a fixed point, whereas B prime is a point on 2 coinciding with B at that instant. Okay, so we can find out the B, but from link 2 you go to B prime and B prime to B, which involves a sliding as well as a rotation. So that means that if you say that okay, this is the frame is attached to the link 2, so as long as the link 2 is concerned, it is also rotating, and the point B is moving in the rotating frame. So we have to apply the rotating frame equations. Okay, so this is the last application here of velocity analysis. So let me just take up one small example, and in the example here, simple geometry. Okay. So I hope this is the mechanism in which we have rod CD on which we have a slider, whereas on rod AB we have a pin C. So that pin C is connected to the slider here. So as far as this link AB is concerned, C is fixed at a distance of 0.4 root 2. Okay. In fact, if you want, I can remove that. Whereas the link on the link 2, the point C is not fixed and C is a slider. So if you want, we can even put another C prime. Probably that's what you were doing it in the exam. That fellow has done it using C prime. So you can also put C prime. So what we need to do here is we have to apply the rotating frame equations. So one thing is that we can even take XY fixed frame as well as small xy. So XY is a fixed frame. So here the slider is moving on link DE, which can also rotate. So this is 1. So that means that this point C, while C is a fixed point on link link 1. Okay, so once you have understood all these things, so the rest of the things is the application of what we have already done using what we have already learned during the analysis of rotating frames. Okay, so now let's do this quickly. So first, obviously, what is given is that only omega 1 and alpha 1. So we do not know omega 2 and alpha 2. So we have to solve for omega 2, as well as we also have to solve for the sliding velocity of C with respect to the rotating frame DE. Okay, so the velocity analysis here. So C, the velocity of C from link 1. So the velocity of C is, we can find out simply by doing omega 1 K cross or CA. Sorry. So this is easy to find, and this is nothing but omega 1 is given to be 3K, and we'll put minus because that's given as a clockwise. And then C with respect to A is nothing but 0.4 I 0.4 J. This is 1.2 I. Okay. So velocity from C from link 2. So which is rotating. Okay, so that we can find out as of course, if you want to take the velocity of D, because now the link DE is whose origin is D. Of course, it's very simple. So it's 0 in any case. And then we have omega 2 K cross or of C with D plus C in the rotating frame. So which we call as, so if you want to put it, this is 0 and this is minus omega 2K, which we have to find out. C with D is 0.4 I. And this one we call as VREL. And this VREL is in the direction of I. Okay. So we have two equations here, 1 and 2. So equating 1 and 2. So we can what all we have to do is that 1.2 I minus 1.2 J is equal to Ki is minus omega 2 into 0.4 J. And okay, so this is what we have here. So you can make the X component and Y component. So solving, we get, I'll straight away put it, we get omega is 3 again VREL is 1.2. So this is as far as the velocity analysis is concerned. Okay, so that I'll leave it to you, how to take I components, take J components, and you can solve for it. Okay, so that is now we are able to solve for angular velocity of 2, as well as how much this slider, how much this point C is really sliding at what velocity. So that we call as VREL. So there's so many ways of saying that this is C with respect to the rotating frame XY. Okay, you can even write it, but as long as you understand, we can even write it as VREL. Okay.
Excuse me, sir.
Yeah.
Sir, how to find the direction of V relative?
V relative, yeah, that's the thing. I have assumed VREL to be, what is that? VREL times I. So what does that mean? This is an assumption here. This is an assumption here. I am assuming that the velocity of V of C is moving in this direction. Okay, it's an assumption. So after solving it, I got 1.2, but I might have got minus 1.2 also. What does that mean? What it means is that it's moving in the opposite direction. Okay, so in all these things, either the angular velocity, angular acceleration, if you do not know, you can assume some direction and go ahead, even the velocity, even the acceleration of AREL. Okay, you can assume that it is in the positive direction or negative direction. Assume. And then after solving it, you will arrive at to be as a positive, which means that it is as per your assumption. If it is negative, that it is opposite to as your assumption, right? Okay, you got it?
Yes,
So,
but can it have like y component also?
no, it cannot. How can it? See, this x is in this direction, right? I'm assuming that x is attached to the rod, okay, and y is up. So, and I know the rod is along x direction, and definitely the slider has to move along x direction. But on the other hand, it's also possible that you can take x, small x, in the 45-degree direction, in which this is moving in the along the rod. So that times you can even have a both x and y component. But one thing is sure that it is moving along the rod. So it has to be along this direction. Okay?
Yes. Okay. Got it. Thank you, sir.
Sure. Anytime. Yeah. So having done that, so this is an assumption. I hope you got it. All these things, all these unknown things, we assume something. We assume we show it certain direction. Okay. So after solving it, we may get a positive value, which means that it's as per assumption. If you get a negative value, it is opposite to our assumption. So, and then now let's do the acceleration analysis. So the acceleration analysis involves more terms. So the acceleration analysis, we can get to the point C using link 1. Okay, using link 1, we can get acceleration of C. Okay, so which means that acceleration of C is what? Can I put it directly now that you are? So I'll put it as minus omega 1 square r CB or C with respect to B, right? So this is, what is this? This is the normal acceleration plus alpha 1 K cross CB. This is the tangential acceleration. So C is fixed on the link AB. Okay, so that's why we got this. So we can simplify this also. So this is minus 3 square, and this is 0.4 I, 0.4 J, and this is alpha 1 is given to be 4 clockwise. So I'll put it as minus 4K cross, same thing. Okay, so this is simple, right? So this is the normal acceleration component, minus omega 1 square C with respect to B. I'm sorry, C with respect to A. Sorry, it's not B. So C, as long as link one is concerned, it's rotating about A. Okay, so this we can simplify, and this is minus 2I minus 5.2J. Okay, so this is how we can write. And then using from link 2 point of view, which is rotating, at omega 2. Okay, we can get AC. So how is that? So AC now is, we have to apply, because link 2 is rotating, and also point P is, while C is sliding. okay, on which I can also write on which C is sliding. Sliding with a relative velocity of v rel. So we can get it now. So this is acceleration of d because this is the origin, right, of the xy frame. So I can write it using xy frame attached to link. Okay, so this is AD plus what else? So we have acceleration. So it is minus omega 2 square. I'll write quickly times R C with respect to D here and alpha 2 K cross for CD. So here, if you have assumed to be clockwise, if you want, I can even put minus here. This is because we have shown it to be clockwise because of assumption. Otherwise, our formula is that it is just alpha K. Okay, and what else? So these are the tangential normal acceleration. In fact, these are, if you call this as another point C prime, C prime is a point on link DE coinciding with C at that instant. And we further move on. So what else? So we have relative acceleration. Okay, so this relative acceleration, if you want, I'll put it as a rel I. Okay, so this is a relative acceleration point. What is relative acceleration? It is the acceleration of C with respect to xy. So this is what we call as, if you want, I can write it as C with respect to xy. And what else? We also have another term, which is the Coriolis part. Okay, right? So now let's simplify this one. So this is 0 and omega 2, we found it to be 3 square times 0.4 I, right? That's all. And then this is alpha 2 is the one which we want to find out. It's K cross RCD is given to be 0.4 I. And what else? This is the relative acceleration. So I'll put it as rel. And I'll put it in the I direction. Okay, I direction. And then Coriolis is the one which we write it as 2 omega 2 cross velocity of C with respect to C prime. Okay. So that's what it is. And let me write, once you remember this, I think make this as 3. And this I'm going to get it as 4. Let me. So we'll continue this, simplified. Simplifying. So we have minus 3 squared and 0.4 I. And alpha 2, we'll put it as alpha 2 is need to be done. K cross I is 0.4 J. And rel is we are assuming it to be in the positive direction towards right. And this Coriolis is the one, I'll put it as Coriolis here. Let me write, simplify it separately. Coriolis is what? 2 omega 2 is given to be, shall I put it here? What omega 2 is? Omega 2 is turned out to be minus 3k cross, what is the velocity? So the relative velocity was 1.2 meters per second, right? And this turns out to be 7.2 minus 7.2 J, right? So this is, so we have all the components. Coriolis, I wrote it separately. So this is omega 2, this clockwise 3 radians, and sliding velocity is 1.2 I, and you get it 7.2. So we have, so equating 3 and 4. So we can equate 3 and 4. Right? So that much you can do. If you want, so it's minus 2I minus 5.2J is equal to minus 3.6I, right? And alpha 2 is minus 0.4 J for alpha 2J and minus 3.6 I here, right? I'm sorry, that's all. Oh, that's done. And ARL and Coriolis is 7.2. Okay, so here, what are the unknowns? So there are two unknowns. So the alpha 2 and ARL unknowns. So we can solve for them. I'm almost done. So solving, we get ARL is nothing but acceleration of C in x small x5 frame is 1.6. And then we have alpha 2 as minus . So which means that the alpha 2 is, we are taking it to be clockwise. So while you got a negative, so which means that you have a positive, you are going in the opposite direction of clockwise, which means that it's counterclockwise. The time is up. I think the time is up, and we'll continue almost this, and we'll start the new chapter as well. I hope I went very slowly. I hope you can understand each step. So here we could get C from this link as well as from this link. Okay. So we have on this, it is simply a fixed point on this, while on this link C is also rotating as well as it is sliding. Okay. I'll stop here.